This session introduces the structured workflow of eco-responsive planning, moving from baseline environmental analysis to the development and evaluation of alternative spatial scenarios. Contemporary ecological planning requires a systematic process that integrates environmental data, climate risk, and socio-spatial dynamics rather than isolated design interventions. The workflow begins with defining project scope and collecting baseline biophysical and socio-economic data, which are synthesized into a diagnostic understanding of the landscape. This foundation supports problem identification, opportunity mapping, and the formulation of ecological objectives. Building on this base, alternative scenarios are developed and evaluated using environmental and resilience criteria, illustrating how integrated workflows support informed planning decisions in complex urban and ecological systems. This presentation is organized to guide you through the full workflow of eco-responsive scenario planning. We begin by outlining the learning objectives and introducing the rationale for structured planning workflows in ecological contexts. The session then moves into framing eco-responsive scenario development and establishing project scope and objectives, which set the foundation for subsequent analysis. We proceed through baseline data collection, multi-layer mapping, and climate and ecological diagnostics, before translating these insights into clearly defined problems and opportunity areas. Building on this analytical base, the presentation addresses visioning and scenario development, leading to the comparison and selection of preferred alternatives. Finally, we explore how scenarios are translated into regulatory and design guidelines, supported by an implementation roadmap, and conclude by reflecting on the role of eco-responsive workflows in advancing regenerative planning futures. This session introduces the core stages of eco-responsive planning, from baseline analysis to the development and evaluation of alternative scenarios. It aims to strengthen understanding of how environmental data and ecological objectives are translated into spatial strategies that inform planning and decision-making. Eco-responsive planning relies on clear workflows because ecological systems, urban processes, and climate dynamics interact in complex and often nonlinear ways. A well-structured workflow helps planners move systematically from environmental data toward actionable spatial strategies, ensuring that decisions are grounded in scientific evidence rather than ad hoc interventions. By clarifying the sequence of analysis, design, and evaluation, workflows also support transparency, interdisciplinary collaboration, and adaptive learning throughout the planning process. At the core of this approach is the connection between diagnostics and scenario development. Baseline ecological and climatic data allow us to visualize existing patterns of vulnerability and opportunity across the landscape. These insights form the foundation for articulating a long-term ecological vision and developing multiple scenarios that explore alternative futures. Each scenario represents a different configuration of land use, density, blue-green infrastructure, and mobility systems. Through systematic evaluations such as using resilience indicators, ecosystem service metrics, and socio-spatial criteria, planners can compare scenarios and derive a preferred direction that balances ecological performance with human needs. Ultimately, eco-responsive workflows enable the translation of scientific knowledge into spatial plans and regulatory frameworks capable of guiding urban and regional transformation. Eco-responsive scenario development focuses on imagining future spatial configurations that strengthen both ecological functioning and climate resilience. To be eco-responsive, a scenario must reflect the dynamic relationships among ecological systems, urban form, and social processes, rather than simply presenting alternative land use distributions. These scenarios anticipate environmental change, integrate resilience principles, and promote regenerative outcomes that sustain ecosystem services over time. An effective eco-responsive scenario emerges from the integration of three analytical dimensions. Biophysical factors, such as hydrology, soil characteristics, vegetation structure, and microclimate dynamics, provide the ecological foundation. Socio-spatial factors such as settlement patterns, density, mobility networks, and demographic trends shape how communities interact with landscapes. Climate risk factors, including heat exposure, flood vulnerability, and projected sea level rise, inform the risk context within which planning occurs. System thinking connects these dimensions by treating cities as coupled socio-ecological systems with feedback loops and thresholds. This approach helps planners explore uncertainties, test alternative futures, and design scenarios that perform effectively under multiple climate and development trajectories. Ultimately, framing scenarios through systems thinking ensures that eco-responsive planning is anticipatory, integrative, and grounded in scientific understanding. Establishing the project scope and objectives provides the foundation for eco-responsive planning. This begins with defining the planning boundary in a way that reflects ecological systems, such as watersheds or green-blue networks, while remaining sensitive to administrative and governance realities. Recognizing cross-boundary flows of water, energy, and people is essential for understanding environmental performance. Equally important is identifying stakeholders and governance structures, including planning authorities, environmental agencies, infrastructure providers, and local communities. Understanding institutional roles and coordination capacities helps anticipate constraints and opportunities for implementation. With this context in place, planners can define clear ecological, social, and climate performance objectives. These goals should be measurable, aligned with broader policy frameworks, and responsive to local needs, ensuring that subsequent scenarios and design strategies remain focused and effective. Baseline data collection is a critical stage in eco-responsive planning, as it provides the empirical foundation for diagnosing ecological conditions and identifying spatial vulnerabilities. The first dimension of baseline mapping focuses on ecological attributes such as land cover, hydrology, soils, and biodiversity. These layers reveal the structure and functioning of local ecosystems. They show where infiltration occurs, where habitats are connected or fragmented, and how water and energy flow across the landscape. Understanding these patterns allows planners to recognize ecological constraints and opportunities essential for scenario development. At the same time, baseline analysis must incorporate urban and socio-spatial data. Urban form, mobility networks, and socio-economic characteristics influence how different communities experience environmental change and how interventions may affect them. Mapping density, transport infrastructure, and vulnerability indicators helps to ensure that eco-responsive planning is socially equitable and spatially coherent. A range of technical tools support this multi-layer mapping process. GIS enables the integration and analysis of diverse spatial datasets, while LIDAR provides high-resolution elevation, vegetation, and building morphology information. Satellite imagery helps detect land cover change, heat islands, and hydrological features. Environmental sensors add real-time microclimate and pollution data. Bringing these data sources together into an integrated analytical framework creates a foundation for evidence-based scenario development and informed decision-making. Climate and ecological diagnostics form the analytical backbone of eco-responsive planning. This stage focuses on understanding how environmental processes operate across the landscape and how they interact with existing land use patterns. Microclimate diagnostics are essential for revealing spatial variations in heat exposure, wind flow, and thermal comfort. Tools such as satellite-derived land surface temperature data, computational fluid dynamics models, and ENVI-MET simulations help identify heat islands, shading deficits, and ventilation corridors that directly influence public health and energy consumption. Hydrological and flood risk assessments provide another critical layer of understanding. By modeling pluvial, fluvial, and coastal flooding, planners can pinpoint areas where water accumulates, drainage systems are overstressed, or sea level rise amplifies exposure. These assessments highlight where adaptive zoning, permeable surfaces, or nature-based solutions are most urgently needed. Finally, ecological diagnostics examine the condition and functionality of ecosystems. Mapping fragmentation, habitat connectivity, and ecological degradation reveals how urbanization has reshaped biodiversity patterns and ecosystem services. Identifying green-blue network gaps help planners integrate ecological corridors into future scenarios. When combined, these diagnostic layers offer a comprehensive picture of climate risk and ecological opportunity, forming a robust evidence base for designing eco-responsive planning alternatives. Problem definition and opportunity identification form the critical link between diagnostic analysis and scenario development. At this stage, multiple data layers, climate risk, ecological conditions, and socio-spatial characteristics are synthesized to reveal where vulnerabilities intersect and where system thresholds may be exceeded. These insights are translated into clear spatial problem statements that explain where risks occur and why, such as heat-exposed neighborhoods, flood-prone infrastructure nodes, or fragmented ecological networks. At the same time, the analysis highlights opportunity zones, including blue-green corridors, restoration areas, and locations suitable for strategic densification. Together, these problem and opportunity definitions provide a focused spatial basis for developing eco-responsive planning scenarios. Visioning represents a critical turning point in the ecological planning workflow because it moves the process from analytical diagnosis toward the imagination of desirable futures. Eco-responsive visioning establishes long-term ecological and climate goals that guide the spatial strategies, scenarios, and regulatory frameworks developed later in the process. These visions articulate how landscapes should function in the future, how water should flow through a district, how biodiversity should be supported, or how a community can thrive in a low-carbon, climate-adaptive environment. Effective visioning must also be grounded in collaborative processes. Design charrettes, scenario storytelling, and participatory workshops allow planners, residents, scientists, and policymakers to co-produce shared narratives about the future. These tools help translate technical data into socially meaningful aspirations while ensuring that ecological goals align with community needs. Examples of eco-responsive visions include carbon-neutral districts powered by renewable energy, regenerative water systems that close hydrological loops, and interconnected biodiversity corridors that restore ecosystem function. By synthesizing ecological science, climate imperatives, and collective aspirations, visioning provides a strategic foundation for developing coherent and transformative planning scenarios. Scenario development requires a coherent framework that brings together morphological, environmental, and socio-ecological drivers. Morphological drivers refer to the structural qualities of the urban landscape, land use configurations, density gradients, infrastructure networks, and ecosystem structure. These elements determine how a city functions physically and spatially, and they form the basis for exploring alternative spatial futures. Environmental drivers add another layer of complexity. Climate projections, hydrological behavior, and biodiversity dynamics reveal how future environmental conditions may alter risks and opportunities. Integrating these drivers ensures that scenarios are not merely speculative but grounded in scientific evidence about climate trajectories and ecological responses. Together, these inputs allow planners to build distinct scenario topologies. A resilient compact growth scenario might prioritize transit-accessible, mixed-use districts combined with microclimate-sensitive design. A nature-based retrofit scenario focuses on restoring ecological processes within existing neighborhoods. Adaptive waterfront scenarios explore flexible, safe-to-fail landscapes that can accommodate periodic inundation, while low-impact suburbanism reimagines peripheral areas through regenerative soils, green corridors, and reduced impervious surfaces. By combining morphological and environmental drivers, the scenario development framework becomes an analytical and creative tool capable of generating robust, eco-responsive alternatives that address climate risk and support long-term landscape resilience. Translating ecological objectives into spatial strategies marks the transition from analysis to design. At this stage, abstract goals such as climate adaptation, biodiversity enhancement, and emission reduction are expressed through concrete spatial decisions. Density gradients, for example, are used to improve microclimate performance by supporting shading, ventilation, and compact urban form. Protecting ecological corridors is equally critical, as continuous green networks support biodiversity and ecosystem functioning while structuring urban growth. Blue-green infrastructure further integrates ecological and climate objectives by managing stormwater, reducing heat stress, and enhancing public space. Finally, spatial strategies must reinforce low-carbon mobility and energy systems, aligning urban form with long-term resilience and sustainability goals. Once ecological objectives have been defined and spatial strategies identified, the next step is translating these strategies into concrete spatial design concepts. This transformation is essential for making ecological planning actionable. Scenario concept drawings serve as a bridge between analytic frameworks and physical design. Green spines, for example, fuse ecological corridors with active mobility routes, supporting both biodiversity and low-carbon mobility. Floodable parks illustrate how public spaces can function as stormwater basins during extreme rainfall while providing recreational value under normal conditions. Eco-blocks and biodistricts demonstrate how entire neighborhoods can be planned around ecological performance, passive cooling, and regenerative cycles. These concepts are tested and refined using performance simulations. Hydraulic models such as SWMM or HEC-ROS simulate how water moves through the landscape under different rainfall scenarios, while microclimate models assess shading, heat exposure, and wind flow. Ecosystem service models quantify benefits such as carbon storage, infiltration capacity, or habitat provision. Together, these simulations provide evidence-based feedback that strengthens the credibility and feasibility of each design concept. Finally, translating design concepts into zoning and development codes ensures that eco-responsive planning becomes institutionalized. This may involve integrating blue-green infrastructure requirements, permeability standards, ecological corridor protections, and performance zoning criteria into regulatory frameworks. In this way, spatial design concepts guide not only what is built, but how it performs within broader socio-ecological systems. Evaluating alternative scenarios is a critical step in eco-responsive planning because it determines which spatial strategies best support long-term sustainability and resilience. A multi-criteria assessment framework allows planners to compare scenarios systematically across ecological, climatic, social, and economic dimensions. Climate risk reduction is often a primary concern, requiring an analysis of how each scenario performs under projected heat, flooding, storm intensity, or sea level rise. Ecosystem service improvements such as cooling, infiltration, and biodiversity enhancement provide additional criteria that reflect the ecological benefits embedded in each scenario. Equally important is the assessment of greenhouse gas emissions, both from mobility patterns and from energy use influenced by urban form. Social equity adds another layer of complexity, ensuring that scenarios do not disproportionately burden vulnerable communities but instead promote inclusive access to environmental and social benefits. Economic feasibility, including life cycle costs and long-term resilience dividends, ensures that proposed strategies are financially sustainable. A combination of tools supports this evaluation process. Multi-criteria analysis enables structured, weighted comparisons of diverse indicators. Ecosystem service scoring provides insight into ecological performance, while resilience indicators assess robustness and adaptive capacity. Selecting preferred alternatives requires a structured process that balances scientific evidence with stakeholder values and long-term ecological objectives. After scenarios have been modeled for climate resilience, ecosystem services, emissions reduction, and socio-economic outcomes, planners compare these outputs systematically. Performance matrices, GIS visualizations, and dashboard tools help illustrate which scenarios deliver the greatest benefits or face significant constraints. However, technical analysis alone cannot determine the preferred option. Stakeholder negotiation plays a critical role in aligning ecological goals with community aspirations, governance priorities, and political feasibility. Participatory evaluation through co-design workshops, deliberative focus groups, and scenario dialogues allows diverse voices to engage with potential futures. This process builds trust, expands local ownership, and ensures that preferred alternatives reflect social, cultural, and ecological priorities. Ultimately, selecting an alternative involves understanding trade-offs and identifying synergies. For instance, strategic densification may reduce emissions but raise concerns about green space access, while ecological restoration may require land use adjustments. Planners must weigh these considerations carefully, emphasizing solutions that perform well across multiple criteria and remain adaptable under climate uncertainty. By integrating evidence, values, and systemic thinking, the selection process supports the emergence of robust, eco-responsive planning pathways. Once a preferred scenario has been selected, the next task is to translate its ecological and spatial principles into regulatory and design guidelines. This step ensures that the scenario becomes an actionable framework embedded within everyday planning decisions and development processes. Zoning overlays are often the first instrument used to codify scenario outcomes. These overlays can designate areas requiring adaptive waterfront standards, ecological corridor protection, or enhanced cooling requirements. They allow planners to incorporate climate risk, biodiversity priorities, and hydrological behavior into binding spatial regulations. Development controls further refine how buildings and neighborhoods perform. By specifying building orientation, massing, permeability minimums, and shading requirements, these controls shape microclimatic and ecological conditions at the block and site levels. Density bonuses or incentives can support the inclusion of green or blue infrastructure and encourage low-carbon design. Ultimately, selecting an alternative involves understanding trade-offs and identifying synergies. For instance, strategic densification may reduce emissions but raise concerns about green space access, while ecological restoration may require land use adjustments. Planners must weigh these considerations carefully, emphasizing solutions that perform well across multiple criteria and remain adaptable under climate uncertainty. Blue-green infrastructure guidelines ensure that stormwater management, urban cooling, and ecological connectivity become integral components of all new developments. Finally, ecological performance standards such as green plot ratio, biodiversity indices, and habitat connectivity metrics provide measurable targets that align with long-term resilience goals. Through this combination of overlays, controls, guidelines, and performance benchmarks, preferred scenarios are transformed into an operational regulatory system capable of delivering climate-responsive and ecologically regenerative urban development. Translating eco-responsive scenarios into practice requires a clear and flexible implementation roadmap. This begins with a phased strategy that sequences actions over time, prioritizing no-regret measures that deliver immediate benefits while preparing the ground for larger interventions. Phasing should be coordinated with infrastructure lifecycles, investment schedules, and projected climate impacts. Implementation also depends on strong institutional partnerships. Effective coordination among planning authorities, environmental agencies, utilities, researchers, and community actors is essential to ensure continuity and shared responsibility. Financing mechanisms and incentives further support implementation by aligning public and private investment with ecological goals. Finally, monitoring and adaptive management allow plans to evolve over time, using performance indicators and digital tools to inform adjustments. Together, these elements transform scenario-based planning into a dynamic and learning-oriented governance process. As we conclude this module, it becomes clear that eco-responsive planning is most effective when it is approached as a continuous and integrated process. Beginning with a rigorous baseline analysis, moving through diagnostic synthesis, scenario development, and spatial strategy formulation, each phase contributes to a comprehensive understanding of landscape potential and vulnerability. Scenario-based planning enables us to navigate uncertainty while grounding decisions in scientific evidence and ecological performance. Equally important is the need for iterative governance. Monitoring, stakeholder engagement, and adaptive management ensure that plans remain relevant as environmental conditions evolve. Looking forward, emerging tools such as digital twins and AI-enhanced performance modeling will accelerate our capacity to test ideas and refine regulatory frameworks. Ultimately, regenerative planning offers a path toward urban systems that not only withstand climate stress but actively restore ecological function and enhance human well-being. This represents the next horizon in resilient and sustainable development.